I can do something like this and show you how I drew mine. Everybody has done theirs, right? So everybody has done their discussion. Yeah, and we're starting with discussion number 2. They say, describe the hybridization of the carbon, blah, 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 basic geometry, whatever. All that beautiful story. So I'm going to start with propane. And my propane actually looks like this. So I went ahead and I started with propane looking like that. I can make this a little larger. I added a lot of stuff to my propane. First of all, I went ahead and I labeled the carbon as sp3. And I saw that all the carbons were the same. And because all the carbons are exactly the same, then I was able to label the hybridization, so I knew that they were all sp3. And then with the magic of color, I was able to highlight bonds that were alike. And so from there I wrote that I had 2 carbons, 2 sigma, carbon sp3 to carbon sp3. And then there were 8 sigmas that were carbon sp3 to hydrogen s. And then I knew that the geometry was tetrahedral, the bond angle 109.5, and I moved on from that example. Is everybody okay? Did everybody end up doing the exact same thing? Yes, yes, yes. I'm missing somebody. I'm gonna say that I'm missing a person. All right. So then that's that. So we'll do the same thing with the next molecule. The next molecule is ethene. And again, I go ahead and I label the carbon, and immediately I know that the carbon there that has a double bond is sp2. So the carbon that is sp2 would look like that. And then with the magic of color, I label the bonds that were the same by the same color. And then I just went ahead and tried to organize that. So we said that because the carbon was sp2, there was a sigma bond in blue between a carbon sp2 to a carbon sp2. We saw 4 sigma bonds that were alike in pink. So we call those 4 sigma carbon sp2 hydrogen s. And then there was a pi bond, and the pi bonds are always made with unhybridized orbitals. In this case, unhybridized p orbitals. So that pi bond is with carbon p. The geometry is trigonoplanar. The bond angle is 120. And I think everybody needs to know all of that. And you know, it's crazy because here I am in Chem 4 and we keep reviewing and bring this back. So really, really, it just doesn't go away. It just does not go away. All right, then we go to propyne. The name of propyne is really ethyne according to IUPAC. The carbon is sp hybridized, a carbon that has a triple bond or 2 double bonds. So a carbon that has a triple bond or 2 double bonds is sp hybridized. So once again, by the magic of color, I recognize that I had 1 carbon sp to 1 carbon sp, so that was an sp to an sp. I also see that there is 2 pink ones that I call pink ones that were carbon sp2. I'm trying to find the same color and I'm just not doing a good job here. Okay, that there were 2 sigma bonds with the carbon sp to the hydrogen s that did not hybridize, and that we had 2 pi bonds, and that those pi bonds that were between carbons p and carbon. That the molecular geometry is linear, that the bond angle is 180, and that's all we need to do. Okay. And everybody okay? okay with all of this? Okay, for the next compound, we're asking that there are the molecular formula is C5H12, that they're saying construct as many isomers as you possibly can. Remember that isomers just need to have a different structure, same molecular formula. So when I went and I did it, I was able to come up with 3. And there they are. Those are your 3 in line angle. I think you have seen this before. You did this in your lab. So review, repeat. I went ahead and a student in the other class wanted to know what this guy is called according to old nomenclature. According to old nomenclature, this is called neopentane. So old nomenclature is neopentane. Okay. Somebody said, well, you wanted them in condensed. So I did that one in condensed and named it. I'm covering some stuff. It gets too crowded, too busy, and people don't learn from too. I wouldn't learn from too crowded, too busy. I don't know about anybody else, but I really cannot. So that would be pentane, line angle drawing, condensed, and its name. So line angle, condensed, and its IUPAC name. I went to this one, and this will be the easiest way to have it in a condensed formula. So condense the CH3 parentheses 2 CH, CH2, CH3. And then now you guys know how to name this according to IUPAC. According to IUPAC, this one would be called 2-methylbutane, so that is correct, 2-methylbutane. I don't know where the name is, but 2-methylbutane. And the very last one, this looks so messed up, but that's possibly the way to be written. Or in other books, you would find this written like C parentheses CH3 4. So oftentimes that is not even done like that. And this one, the IUPAC name will be 2,2-dimethylpropane. Okay, so 2,2-dimethylpropane. Everybody okay? All right. They want us to do C6H14. And I started with that for C6H14. And I came up with, oh, okay, wait. I want to be totally systematic. So I tell students, this is what happens when everything is done. So the easiest thing to do is to first line it all in one way, right, all 6. And then the next way is to go ahead and have 5 carbons in a row, right? So from 6, you would go to 5 carbons. And when you go to 5 carbons, you would have 1 methyl that you have to attach, right? And that 1 methyl that you have to attach, where could you attach it? Is everybody okay with this drawn, or do you want me to like draw? Do you want me to put it on paper? No, everybody okay? All right, so after you do 6 in a row, then the mentality is that you'll take 1 carbon off, and where would you put that 1 carbon? And you can see that that carbon can go from carbon 2 to carbon 3, and then you would have your 2-methylpentane and your 3-methylpentane, okay? I don't think there's any other place where you can put that methyl and be a different compound, okay? So then you kind of go back to the same 6, and now you pull 2 carbons off. Is everybody? So after you do 6, after you do 5, now you're thinking you're doing 4, and you have 2 carbons that you took off. Where will those carbons go on 4, right? So I think I can put them both on the same carbon. What would we call this guy now? Very good. This guy will now be called 2,2-dimethylbutane. Or I can put them on different carbons. Exactly. Then this guy will be 2,3 dimethylbutane, right? So this will be 2,3 dimethylbutane. I don't think I have any other place to put them, right? Can I do anything else? Can I do anything else? No, can I take two? Can I do this? Sorry. Can I do this? So everybody's agreeing that I could do 4, but can I do this? So I have 4, and instead of having 2 carbons that were separate, can I just put an ethyl on 1? Because I can, but is this a different compound?
No.
It changes it now to a 5. So now it'll be a 1, 2, 3, 4, 5. So now we're back at this guy, that it will be the 3-methyl pentane. So the nice thing about naming compounds is that you can see that if the name is the same, even though the structure looks so different, it would still be the same kind of a compound. Is everybody okay with that? Is everybody understanding what I'm trying to get at? All right. Yeah. Ugh. I mean, the condensed formulas, I hate them too. So she goes, how do you do the condensed formulas? Well, for this one, which is the hexane, the condensed formula here will be the CH3 and then 1, 2, 3, 4. So CH2, 4, CH3. Okay. Then for this one, then would be CH3, 2, CH, and then CH2, 2 CH3. Right, so we have 1, 2 with a CH, with 2 CH2 with the CH3s. For this one, would be CH3, CH2, CH, parentheses, CH3, CH2, CH3, like that. I hate when there's one. There's everything on the first test. First test is like, oh, no way. All right, for this one, how would we draw condensed formulas for this one? CH3, 3, C, and then CH2, CH3, right? I don't even want to know what I'm going to do with this one. What are we going to do with this guy? They're telling me CH3, 2, CH, CH. I'm following what they're telling me to do. I agree. I like it. Yeah, you just go carbon by carbon, exactly. You just go carbon by carbon. Because it's like you're looking at this carbon, and that carbon has 1 CH3 and 2 CH3, so there are 2 of them. And there's a hydrogen here that we don't see, so that CH is bonded to 2 methyls, and is bonded to this carbon that has an H and 2 methyls. Yeah. Kind of whacked, but yeah. Follow along this. Remember, I didn't make these rules. You're kind of following along the, kind of like the way you name a compound. So like you're naming a compound like carbon 1, 2, 3, 4. So this carbon 1, 2, C3, 4, which is the skeleton of the molecule. When you get to that carbon, you see that you have two groups that are alike, and then you put them together in parentheses. So. All right, now they want you to go ahead and look at number 3. And number 3, they want you to do 3 compounds with that molecular formula. And so by now, we know that this C3H8O, what is that telling you of that compound, that you have 8 hydrogens? What is that saying of the compound? That it has only all single bonds? Does everybody agree? Well, if you go to the parent alkane, remember we said C3, and then the formula was 2N plus 2. So if you have 3 carbons, times 2 is 6, and 2 more is 8, so this was like propane. So if you have them all single bond and there's only 1 oxygen, the option are that you have in alcohols that were all single bonds. And so this is what I want to do. So if I do it like this, how many places do you have of putting that OH? I think I can put that OH in carbon 1, or I can come out here and put it in carbon 2, and these will be 2 different alcohols that I have from there. Since now you know so much, this guy is called a primary carbon, so this guy would be called a primary alcohol. All right, so that's one option. Or you can come over here and take a look that that carbon was secondary, so this then will be a secondary alcohol. So that's one of the ways that you can have, right? Is there any other way that you can have an alcohol? Is there any other option with 3 carbons have an alcohol? I think the answer is I don't think so. Okay, I don't think so. And now we're going to take a look at what happens if you actually have ethers. Ethers are also ROR. And since I have a total of 3 carbons, I think the only way that I can split 3 carbons is in 1 and 2. So I can put the oxygen in here, and 1 carbon to one side and 2 to the other side, and that will be the only way that I can do this. So there's 1 carbon here, and 1 and 2 over here. So this will be the line angle for that ether, that I can do it like that. Or like Amber, you're Amber. We call her something else. Or like Amber, it's been a weekend, you know. I mean, it's easy to forget things for now. By next week, it'll be there. Or then she says, what if you go ahead and make it into a ring? She says, can you make it into a ring? I said, okay, well, let me try. Okay? So you always want to say, okay, you want to try. So I want to try. I have the oxygen, and I have 1 carbon, and I have 2 carbon, and I have 3 carbons. So I have that, right? Now remember, in order for this to exist, you have to have the same molecular form. So when I count, that carbon has 1 and 2 hydrogens, 3 and 4, 5 and 6, so it's not that, so then I couldn't put it into a ring. Is everybody there? So you really, whatever structure you draw, which is fine, whatever structure you draw, that structure needs to have the same number of atoms of each element in your original compound. It doesn't matter who you're attached to, because in this one you had 1, 2, 3 carbons, and then you had 1, 2, 3, 4, 5, 6, 7, 8, and the O. You need to have that same formula.
So you can put the hydrogens on the oxygen?
You cannot put hydrogens on the oxygen. The oxygen has 2 simple bonds. So you cannot do that. Oxygen. Yeah. Right? I mean, the important thing is that when you calculate, like this one had 1, 2, 3 carbons again, and I had 1, 2, 3, 4, 5, 6, 7, and 8 hydrogens and the O. Or here I had 1, 2, 3 carbons, and 1, 2, 3, 4, 5, 6, 7, and 8 hydrogens and the O. So you need to have the same molecular formula. And the oxygen really just normal, common oxygen. There are only 2 common oxygens. Your oxygen can have 2 single bonds and the 2 lone pairs, or the oxygen can have a double bond and the 2 lone pairs. You don't want to be blowing up the octet. You don't want to confuse their major and minor resonance with typical bonding patterns, all right? Maybe that's where the story comes in. You're welcome. All right, so let's take a look now at the C3H6. When we look at this C3H6, oh, forget that. We're not going to do all that. Forget the condense, that's too complicated and it's not consuming and it doesn't really matter. The condense is when I'm typing for you. I guess I'll do this one, just for one moment. She wants the condensed structure. I think what is important about the condensed structure is that in this case, you're starting over here. So it will start like this, and this makes no sense, which is this one probably will never appear in a condense. This probably appears in a condense, where you would have a CH3, a CH parentheses OH, and CH3. I don't even think this one appears in a condense.
Could you do parentheses 2 since it's all attached to CH?
Usually it doesn't. They usually have it in that. All right, when we get to the C3H6O, I think already we see that there are 2 less hydrogens. 2 less hydrogens than before. So the moment that there are 2 less hydrogens, you start seeing the beginning of an unsaturation, or 2 less. So Amber, for you, I think typical, this could be your ether, like you want it. So I can go ahead and do my carbon, my oxygen, my carbon, and my oxygen. And this one works, because I only have 1 and 2 and 3 and 4 and 5 and 6. So this formula fits that structure. This one is perfect. Okay, so for the C3H6, this would have worked just perfectly well. I guess I can also have maybe like something like this. I'm gonna draw crazy. This is a typical aldehyde. The majority of the time they draw it like this. I have such a problem with that. I hate to have that double bond hanging, so I usually put my little hydrogen there. Again, take a look that you have the molecular formula. C1, 2, 3, and there'll be 3, 4, 5, 6 hydrogens. That's an aldehyde. Or I can come here and put a ketone, and a ketone will be this carbon to carbon to carbon, double bond O. And then you would have your 3 hydrogens here. I actually want to make sure that this time I really do the condense. This condensed would just be this. That's condensed. That cannot be open up and CH2, CH2, that's that. So you cannot do typing as a straight line. That would be condensed for that ring. Condensed for the aldehyde would actually look like this. You would have a CH3, you would have a CH2, and the aldehyde condensed is a CHO. The alcohol that you see was a COH. So alcohols are COH, aldehydes are CHO. So it would look like a CHO, like some name or something. CHO. Yeah. The ketone in a condensed, the ketone in a condensed will actually look like this, COCH3. And that's kind of crazy because people don't know what they're going to do there. And that's a C double bond O. There's no other way of doing this, so that's C double bond O. I think I have one more. And it's when we have the carbon-carbon double bond. So we can have this. How many places can you put the alcohol and be totally different? If you put the alcohol here, it's different than if you put the alcohol here. It's different than if you put the alcohol here. Yeah? And even this one, you could put the alcohol that way. So there are four different ways. These guys are called unsaturated. Unsaturated alcohols.
So what do you
This one does, because this could be the cis or trans, so they're going in opposite or the same. In this case over here, it doesn't matter. So when you have the OH bonded directly to the double bond, like in this case, when you have the OH bonded directly to the double bond, when you have the OH bonded directly to the double bond, when you have the OH bonded directly to the double bond, did you see all those three? These are called ene for the alkene ol. The chemistry totally weak, wild, insane. We end up Chem 4 with that chapter 22. That chemistry is unique. So we'll refine that when we get to the chapter of the alcohols. We'll give another layer of information when we get there. Okay. I think I'm done. So when they said to draw five, we had 1, we had 2, we had 3, we had 4, and we had 5, I guess. Did anybody come up with any other one? Any other one? Well, I guess just like you did this one with 4, right? I guess you could have done something like this back up here. You could have done this one and put a methyl. Remember, the whole idea is that you always have the same molecule. Anybody came up with anything else? Something else differently? La, la, la? All right. So I am going to go as crazy fast as I can, and I hope that everybody kind of follows me. And I ask you to start with the 8. They're saying there are 8 alcohols. So C5 is C5H12O. And they're wanting 8. They're saying there are 8 alcohols. The only way this is going to work is if every time you go to, remember how we went to pentane? And in pentane we said that there were how many sets of equivalent hydrogens in pentane? How many sets of equivalent hydrogens in pentane? That one, pentane. Sets of equivalent hydrogens. Is everybody seeing 3? Well, let's see. If I put the OH here, is that the same or different as if I put the OH here? Are you seeing that? So I go from 1 to 2 to 3. Go from 1 to 2 to 3. So that has 3 different alcohols. You go back and you go, guess what? There were 3 sets of equivalent alcohols in pentane. Yeah? All right, we're going to go through how else can you put 5 carbons. I think you said that this was another way of putting 5 carbons. So I'm gonna do them like this. And I'm gonna put the OHs like so. Same or different? Same or different? Same or different? And everybody see that they're all different? They're all different. This will be a 1, 2. We don't even know how to name it. That's not what you have to do. But the alcohol is on 1, the methyl is on 2. Over here, the alcohol is on 2, the methyl is on 2. Over here, the alcohol is on 2, the methyl is on 3. And over here, the alcohol is on 1, the methyl is on 4. Did you see the numbers? All different number combinations, all 4 different compounds. Back up, you had 4 sets of equivalent hydrogens in the 2-methyl butane. And so there were 4 sets of equivalent hydrogens in the 2-methyl butane. Okay, the very last one when you came in and you did this, you did that. That was the last option for, so all I did, I created the, so all I did, back up, back up, back up, back up. This you have in your, supposedly that you have in your lab notebook. When we were saying you have 3 isomers of C5H12, you should have had that. When we start introducing alcohol, it gets much bigger, and the alcohol could have been there, and it would have been the same if it's here, here, or there. All the same, all the same. Yes? Usually when you have, no, we're not doing what this specials. Okay, is everybody okay? Is everybody still okay? Okay, we have the same molecular formula, but now, we have the same molecular formula, but now they want 6 ethers. Ethers are ROR. They want you to have 6 ethers. Well, if you have 5 carbons, the best you can do is split them up. In 1 and 4, come up with 5. Right, my thoughts are, if I have 5, an ether is, excuse me, may I put in, I would have a 1O5 carbons, right? And I can have a 2O3 carbons. I hope this is not crazy confusing. I'm going to start with the 2 and 3, that would be the easiest one. And the line angle drawing is very confusing here, okay? So line angle is very confusing, but I can see that if I have 2, I can do this. And this will be like an ethyl propyl ether. And I can have my hydrogens. I'm not putting them in. Gets very messy. Right? Can everybody see that this could be an ether? This one will be really easy in a condensed that you love so much that I hate. This could be the CH3, CH2O, CH2, CH2, CH3. Or now you saw that there was only one ethyl. There was no other way of doing an ethyl. There was only one. And there was 2 ways of 3 carbons. So you could have the propyl, or you could have the isopropyl, like that. So the propyl could be attached at the primary, or the propyl could be attached at the secondary. So that's your only combination of 2 and 3. That's what I meant by 2 and 3. When you have 1 and 4, when you have 1 and 5, is that why people were looking at me weird? That could be what people were looking at me weird and not saying a word. When you have 1 and 4, 1 and 4. Okay, so 1 and 4, I can do this. 1, 2, 3, and 4, and that was the butyl. Right, so this was the butyl. This was Or I could have, and this was sec-butyl, or that was sec-butyl. Or you could have, and this was isobutyl. You have to memorize all of these, by the way. But it came at a good time in lecture and discussion that we reviewed. Bless you. Or you could have the tert-butyl. Everybody okay? Isobutyl is if you were to put your eye somewhere, it looks the same. I mean, like if none of this is here, you could see that you would see something that is the same on both sides. The sec-butyl was that secondary carbon that was a new attach. Gotta memorize them. I can try to make it as easy as I can, but you gotta memorize them. Okay, we're looking at the 8 aldehydes of C6H12. So they want 8 aldehydes, C6H12. Oh. And they want 8 of these, and they look like that. I think I'm gonna go with pencil because, you know, life is gonna get kind of messy. I don't know if I did a better job here. All right, so I think the best I can do is go 6, 1, 2, 3, 4, 5, 6, and I'll put the aldehyde at that end. That will be the simplest way to begin, right? The simplest way. And then you go ahead and you take 1 carbon, right? And then you go ahead and take 1 carbon, and how many places do you have of placing it? It's very hard for me to start out like so. I will try. And that's 1, 2, 3, 4, 5. Okay, so how many places can I put that methyl that I took out? If I put it here, would that be the same or different than if I put it here? Would that be the same or different than if I put it there? Aldehydes are like at the very top of the parent, so he will be always number 1. So that will be carbon number 1 always. So then all of a sudden the methyl is on 2, or the methyl is on 3, or the methyl is on 4. So there are 3 different places where you can put them. Yeah? Everybody okay? Can I put it at the end? If I put it at the end, I'm back again to the hexanol at the top. Okay, I'm gonna do 4. I'm gonna do 4. And now I have 2 methyls. 2 methyls. I guess I can put them all up and down, or I can go ahead and put them, bless you, here and there. So I have 1, 2, 3, 4, 5, 6. Or I guess I can do, what did you say? An ethyl here. I think that's what you said, right? Am I missing one?
Could you put 2 methyls on carbon 2?
So I put 2 methyls on carbon 2.
I mean, carbon 3.
There we go. How about putting 2 methyls on carbon 3? There you go. So I have 1, 2, 3, 4, 5, 6, 7, and 8. So are you seeing the systematic way of doing things? Systematic, that you really start always with a 6 strung along, then you do the 5, and you're taking methyls, and you do 4, you take methyls or ethyls. You really want to have some consistency, okay? I'm going to skip all the way to the carboxylic acids, because the only difference between a carboxylic acid and an aldehyde is 2 oxygens. It's 2 oxygens, so it's all the same, everybody, all the same. But now, if I want the 8 carboxylic acids that look like that, what am I gonna do? Oh, I'll put an O. Oh, I'll put an O. Oh, I'll put an O. And 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 I'm done. I'm not gonna redraw all this. Are you mad? We're done. Those are my 8. All I did was squeeze in the oxygen. Right? All you're doing is squeezing in the oxygen. Is everybody okay? We're good? Look how I'm going to cheat. I'm going back here. They wanted ketones. They wanted ketones. And they want 6 ketones. They want 6 ketones. And the molecular formula is C6H12O. Guess what I'm going to do? C double bond O. And that's 1. C double bond O. And that's 2. And here I'll have a C double bond O. And 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 I'm done. We're not going to redraw all this. Everybody, we're not going to redraw all this. The difference is that you substituted the oxygen. See what we did? We substituted the oxygen for the carbonyl. The ketone is the carbonyl. But the rest looks exactly the same. Okay, it looks exactly the same. That's letter, this one was B. And now I went ahead and I squeezed D in there. Let's take a look at the esters. The esters, not so easy. Okay, let's take a look at the esters. They want you to go ahead and come up with 9 esters. And the molecular formula is C6H12O2. And they want 9 esters. And everybody knows that esters are like this. And there are R groups here and R groups there. Right? Everybody knows this. Yes? Okay. So I'm going to do the same thing. I need 6. So that's 1 carbon. I'm going to have a 1 and a 4. 4, 1, 5, yes. All right. So I can do it like this. I'm going to put that here. The butyl. Is that the same, or different? As if I do this. Same or different? They the same or different? These guys are different. The parent alcohol would be, the parent acid would be this. So this will be the parent acid. And this is the attachment. The parent acid here would be this. And this is the attachment. So with every single one, you're going to end up with 2. Which means what? If you have a butyl here, what else could you have? You could have a butyl, You could have a sec-butyl.
ISO.
You could have the isobutyl. You could have the tert-butyl. And the same over here. So just from this combination of 1 and 4, there are 8 esters like this. So everybody. Maybe you never would have come up with this without me. That's not the point. Okay, everybody. So don't jump off the bridge because you never thought of that. Okay, all we want you to do is just think of it this way now. Okay, so that's the big difference. So when you go ahead and you rotate it, we end up with all of that. So the same thing is we do 2 and 3, right? If we're doing 2 and 3, 2 and 3 we will have a CH3, CH2, the C double bond O, and then over here we have a CH2, CH2, CH3, and then swap. Everybody swap. Is everybody following? I mean the swap like this. Yeah? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the big molecule goes like that. This is like where the whole acid was. This is the acid. This is the substituent. Over here, this was the acid. And this was the substituent. Do you see that they're different? And everybody see that they're different? And just like you have the propyl, you can also have here the isopropyl. So 4 more from here. 4 more esters from here. Okay, time to go. Chop. Time. All right, when I see you all again, I know I'm not done. I know we're not done. When I see you all again, people come with all their lab gear. All their lab gear, all right? So you're coming with all of your lab gear. And I see you all again at once. Your lab notebook, your lab book, so that we can talk about the experiment.